right. So what do you want to what do you guys want to do today? What do you guys want to do today? Huh? I think most of you are now kind of aware of how to do the coordinate transformation. Correct? One of the other things you should have done in last class or last exam, yesterday's exam was, did you do the lat long problem? Mm-hmm. I did it on my homework. I looked it up to do it on homework, and I forgot how to do it. Okay. So what is the, see, you have to understand what is the importance of lat long. Or right accession, right declination. What do you think is the importance of that? Latitude and longitude. The orbital elements will also do that. What is no, the right accession and right declination, or latitude and longitude. See, what you can do with that is, you can actually, if you calculate that continuously, you can do a ground trace of your satellite, ground track of your satellite. You see it? Given the orbital elements, if you calculate the latitude and longitude, you can express where the satellite is at a given time. Okay. We'll do that. We won't discuss that for this class, but what we'll do is we'll try to discuss that in some other class. It's the ground track of a satellite. Okay. And if you're looking at ground track, can you relate any of the angles of the orbital elements, or any of the what are the orbital elements? Right. Right. So if you look at the angles, the cap omega, which is right accession of the ascending node, or accession of ascending node, that should give you the longitude. Do you see it? No? Mm-hmm. Longitude on the, what longitude on Earth? let us hang on. Right now we are looking at ground tracks. It is section 4.8, page 244. All right, let's skip ground trace for now. We'll come back to it in the next class. Let's go on to chapter 5. Okay. So chapter 5 is preliminary orbit determination. Okay. Have we done orbit determination? Yes. Huh? Did we do orbit determination? Not the topic. Huh? We did orbit determination. We discussed how to do it as well. Yes, that's what is orbit determination. So orbit determination is nothing but determining those elements, right? So what we looked at was your midterm exam. If you remember, see, let's define or let's understand what orbit determination means. Orbit determination means determining the orbital elements given, right, something like that, position and velocity vector. So you're given, or you know, Earth-bound observations. Okay. And you require to find orbital elements. Okay, this is orbit determination. So what was the first method we discussed? You understand Earth-bound observations? Okay. Huh? Relative to the Earth. Can you observe measurements made from Earth? So these are measurements. Observations are just measurements made from Earth. Okay. Can you make these measurements from Earth? Huh? Can you measure the semi-major axis of an orbit? You cannot do that. You cannot measure eccentricity. Okay. You cannot measure I, or inclination of the orbit. Okay. You cannot measure cap omega, omega, or theta. What you can measure is, let's say, you can measure the position, right? Velocity. Can you measure the position of an orbiting satellite? Position relative to your reference on Earth. Yeah, something like radar. You can do that, right? So that will give you the position, which is R. It could be in ECI frame, it could be in your own frame, the instrument frame. You can also measure the velocity of such an orbiting body. If you keep shooting a radar or a LiDAR, it will give you, if you know the time of flight, you'll come to know the velocity. You know what cops do? Cops. They have a radar shooting at you, right? So that is a way they measure your speed. So you can do that to a satellite as well when it is doing this. So it's essentially, what is it? It's triangulation principle. Okay. So you have this, right? You do this, and you do this. You can measure this, right? If you know this angle, you'll know this angle because you're shifting your radar or LiDAR. If you know this angle, you can always measure this arc, and you know the time which has passed from this point to this point. So you can easily measure the velocity from ground. Okay? Huh? Okay. So what we looked at R and V. The first orbit determination problem was, given R and V, you could calculate all of these. Okay. We're going to look at something called Gibbs. Okay. Now Gibbs orbit determination works like this. You given R1, R2, and R3, and you're required to find A, E, I, So again, if you give me the MATLAB implementation of this, you'll receive 2 points. Okay? 2 points is a lot of points, right? 2 points of your entire 100%. Okay? So give me the MATLAB implementation, and you get 2% of your points, which is extra credit. which I'm sure you can use. So what is this method? Now, given these three vectors, what do you understand? What is this three vectors mean? Position of? Yeah? Orbiting body. You can say orbiting body. It's not orbital element. You cannot. What do you mean by position of orbiting element? Orbiting body. Okay. So this is position of an orbiting body at three instances of time. Okay, make sense? Yes.
The previous one we did was for given a position vector and a velocity vector. So do we need to do another one where we is that another 2 points?
Right. So that was 2 points. This is what was the first one? You were given R and V, right? Here it is different. It is you're given three position vectors. Okay. If you're given three position vectors, what is the immediate thing you observe? Huh? That I don't think you can observe that. What is the immediate thing you observe? Right, three positions, but all the three positions are? Huh? True, what else? So you have this, and let's say you have this. Okay. Don't guess. All right. So what is special about these position vectors? What is the word you're looking at? The word you're looking at is these are coplanar vectors, right? Right. What do you mean by coplanar vectors? Correct. They have to be on the same plane because this orbit is a plane, right? That is one of the fundamental foundations of this orbital mechanics. It is always a single plane, right? So these vectors have to be in a single plane. What is the first thing you're going to do when you're given this? You want to verify whether the vectors are coplanar. How do you verify whether the vectors are whether three vectors are coplanar? Three vectors.
Yes.
The first step one is you have done this. You have done this as part of your exam, first exam. You've done this as part of your homework. The first thing you're going to do is verify whether the vectors are coplanar. And how do you do it? No idea? Huh? You cannot take cross product of three vectors. It is three vectors. You do this. You do the scalar triple product. Right? What do you mean by scalar triple product? You have R1 dotted with, right, this should be equal to, it should be equal to 0, right? If you take R2 cross with R3, huh? What do you mean scalar vector? What are you saying, Ms. Davis? Are you in the class or where are you? It will be a vector orthogonal to both these vectors, right? If you take R2 and R3, this vector, the cross of that two vectors would be this vector, right? It has to be this vector because it has to be perpendicular to both these vectors. Now, if you take the dot product of these two, this vector is perpendicular to all three vectors. And if you take, what is the dot product of two orthogonal vectors? 0. Right? So this, you have to, you can verify this. Okay? If three vectors are given, if they are coplanar, their scalar triple product has to be 0. Okay? So that is how you start verification of code. In step 2, so the first, even in your MATLAB implementation, all you have to do is, so for example, how do you implement this? This command. Right. So if you look at the specific MATLAB implementation, I'll just give you this one. You do this. You use this specific command. You do dot in brackets R1, comma, cross R2, comma, R3. This is a straightforward implementation of these. Okay. So if you say this will give you the answer. Okay. Now what is going to happen here is it is not always going to be exactly equal to 0. Keep that in mind. There's a MATLAB will compute up to 0.000000, maybe e to the power of 10, 20, I don't know. So it may not end up 0. You have to have a cutoff. If it is less than, let's say, 0.00000001, then it is 0. You do something like that. You understand? Okay. So you can check with this. Now, as Sammy said, you could have done just this. Assign this another variable. Let's say R4, right? And then take the dot of those two. You can do that as well. But MATLAB lets you implement, go with direct. Second step is you can write R2 is equal to C1 R1 plus C2 R3. See, when you have three vectors, okay, or three lines in a plane, you can always express them like this. is not a, yes, it's a constant. It's a scalar constant. Okay, this is essentially triangular inequality or equality. For example, if you're given these two, see, you take all these three, and you can form a triangle, right? You just move this around. You have this. You move this here, right? This can be expressed. So if you just keep going, this can be expressed, R3 or R2 can be expressed in some scalar as a linear combination of those two. This is a linear combination, correct? So you can always express one vector as combination of other two vectors, linear combination of other two vectors. If they are in a plane, that is the condition. If they are coplanar only, then you can do it. If they are not coplanar, then your triangle becomes, it's a 3D triangle. It's not a 2D triangle. It's 3D geometry. So that time the rules are different. Okay. So step 3 is you do this and you calculate C1 and C2. All right. That is step 2. All right, we'll come back to how we calculate C1 and C2. The next step is, let's not take these as steps, okay? Let's just see the rationale behind calculating this, and we'll summarize those in steps, which will be your MATLAB implementation, okay? So you have V crossed with H is equal to mu R over Where did we get this equation from? Any idea? Hmm? Right, I think you have used it. You used it when you did this. You remember? Hmm? Right, when we are trying to find eccentricity, you used part of this. Okay. Hmm? So if you take this, you do H crossed with mu H crossed with R over R plus, is this E? Has to be E, yeah. Have H crossed with E. Yeah. So if you just move around, I think you'll realize that that is what it was for E. Okay. This is from orbit equation derivation. Okay. When we started deriving the orbit equation, we arrived at this. I think at step, the output of first step, there were two stages of that derivation. The first stage of that derivation was this equation. Okay, and you used it to find E in your orbit determination. So we have done this. So we have, what is this? How can you express this? The left hand side, if you look at the left hand side, you can express it as back minus cab. Okay, so you have V H dotted with H, right? Minus cab, it is H C A V. H dotted with V. Okay. So you can say left hand side is equal to this. Okay. It is equal to V into H square. Okay. Why is this 0? Right. They are orthogonal because V has to be in this plane, right? H is coming out. So they have to be orthogonal. And the dot product of this is 90 degrees, cosine of 90 is 0. Okay. So this is V H square. All right. you can say just do a little bit more and end it and stop it here. You have V is equal to mu over h square h cross r. Right, we'll get to that. See, we have found an expression for V, but if you look at this, we still don't know. So what is known here in this equation? What is known? It is not known because we don't know V. We only know R. Okay, this R and this R. And we know mu because we know the central point. Obviously, we don't know E, right? Because we're trying to find that. Correct? Right. So if you look at in the perifocal frame, E is equal to E into V, right? And H is equal to H into W. You agree with that? What is the P direction? Perigee or the periasis direction, okay? It's this direction. Our eccentricity vector is always, we said, it's always in that direction. So the E is magnitude of eccentricity. E is the direction. You express it like this. The magnitude into direction. H is again magnitude H. W direction is coming out, right? PQW. P, Q, and W. Alright? So you have V is equal to mu over h square HW crossed with R over R plus H cross E. What is W cross with P? Any idea? W cross with P? Q, or it's minus Q. It's not or, actually it's minus Q. It has to be minus Q because you have, see, you have P is what? Q crossed with W, right? This order has to be maintained. P, Q, W, or Q is W crossed with P. You cyclically change it. Okay? So you have W crossed with P. You're right, actually. It is Q. It is W crossed with P is Q. Okay? This order has to be maintained. So you have this. mu over h into w crossed with r over r plus we'll do this. We'll stop here. V is equal to mu over h. Okay. It is w crossed with r over r. Okay. We'll continue from this point onwards in next class. Yes. It is vector, yes, you're right. Because it has to be vector. You have two vectors. This is a vector, this is a vector. So eventually it has to end up with